Last time we talked about linear geometry in R3. Lines and planes were the linear or flat objects in R3. So the equation of a line had one parameter, whereas the equation of a plane had two parameters. And in fact, this number of parameters is what differentiates between a curve and a surface. We are going to study non-flat geometry in R3. All of the special results we're going to talk about are based on some curves from R2 called conic sections. Conic sections are the curves that you get when you take a cone and you intersect it with a plane. I've got some images here representing different conic sections. Here's a cone. When you have a plane intersecting it perpendicular to the axis, it generates a circle. The curve that you see highlighted in this reddish color, it's going to be useful to have the Cartesian equation of these curves. So the simplest version of a circle is this, and if we place it on an xy axis, the equation of a circle through the Pythagorean theorem is given by this. Now, the center of the circle is located at the origin. It's possible for you to move the center around through completing the square, but we won't get into that here. Remember that the radius of this circle here is given by the value of k. An ellipse is a different type of curve. Instead of intersecting the cone perpendicular to its axis, you now intersect it at some angle. So generally speaking, the equation of an ellipse in Cartesian coordinates is going to look like this. It's always equal to 1. If it's longer on the x-axis, the value of a is larger than the value of b. So the axis intercepts represent the a and the b values there in the denominators. If you wanted to have an ellipse that was longer in the y-axis, then you would have the value of b larger in the denominator than the value of a. There are two other curves that are also very important. You've seen a parabola before, and this is what happens when you intersect the plane parallel to the side of the cone. Now, the simplest equation for a parabola that we have in Cartesian coordinates is y equals x squared. There's this point down here at the bottom. This is called the vertex of the parabola, and that lives at 0, 0 when we've got this. Now, finally, the last curve is something called a hyperbola. When you take a plane and you keep it directly vertical and it cuts out the cone in these double curved patterns. It almost looks like two parabolas, but the curviness is not quite the same as with a parabola. You can have two different equations of a hyperbola in Cartesian coordinates. If you've got a hyperbola that intersects the Cartesian axis here, axis intercept represents the quantity with the positive sign here. So this intersects at a and negative a. The variable with the negative does not have any axis intercept. So for example, if x is 0, it's impossible for negative y squared to equal 1. If your hyperbola is going to intersect on the y-axis, then what you would have would be a slightly different equation. You would have y squared over a squared minus x squared over b squared is equal to 1. Intercepts would be at a and negative a. So what's important is that the term that is positive is always the variable with the axis intercepts. Now, generally, conic sections kind of look like this. They end up being one of these expressions. Now, depending on how you put their center, etc., a conic section is some sort of curve that has a Cartesian equation like this. The constants a, c, d, etc. are dials that you turn to turn things positive, negative, stretch, etc., etc., etc. Now, when you generalize anything to a third dimension, you have a lot of freedom. We're going to talk about two special cases, something called cylinders and something called quadric surfaces. Now, both of these are examples of surfaces, but they are very special cases. What's going to be very useful for us is something called traces. And a trace is a set of points obtained when a surface intersects a plane. We are usually going to talk about coordinate planes only. So we'll talk about x equals a constant, y equals a constant, z equals a constant. So the first type of surface we are going to talk about is what's called a cylinder. So if I talk about a certain curve, this curve lives in R3. If I were to take this curve, I'm going to say that it's captured in some plane. So there's going to be a line L that is not in the plane. I'm going to have this line intersect the plane. We are going to assume it intersects perpendicularly. So if I were to take any point on this curve and then draw a line that's perpendicular to the plane, it's going to extend out like this. Take every single point and then take every line that is parallel to the first one that you drew. And if you go through and you construct all of those lines, what you're going to end up with is a surface called a cylinder. It's essentially copying and pasting that curve all the way down the line. Think of a sheet of paper that represents your initial curve here. Every one of those curves is a copy of the original, and then you've got all of your lines going through this way. Sometimes these are called mesh lines or grid lines. It's essentially a sheet of paper that is not flat, but it has no depth. And what we're going to talk about here are common, and I should say easy cases of cylinders. And this is going to be when we have an equation in the three letters x, y, and z that is missing one of the variables. This ends up producing a cylinder in that missing variable direction. And it extends in the missing variable direction. So for example, if I give you the equation 4 minus y squared, and remember that we are now in R3. If I were to just think of this as a two-variable function, the curve that I'm going to be given here is z as a function of y. This ends up producing a parabola. It's an upside-down parabola, and you know that it intersects at 2 and negative 2. So the idea now is that we're going to put this on a set of 3D axes. I've still got my parabola like so, but what's going to happen is I'm going to extend it in that missing variable direction. So I'm just going to extend it in the x direction, parallel to the x direction. And this extends the whole way. Now, I've only drawn half the parabola here. There's the other half as well. And so what ends up happening is you just have this cylinder. It's a sheet of paper that contains all of these copies. So it's like making a tent, the surface of a tent. Another example of a cylinder is y squared minus x squared is equal to 1. This is a hyperbola. If I were to think about the curve in the xy plane, this would be the hyperbola that touches the y-axis at 1 and negative 1. And now I'm going to extend this to 3 dimensions, the usual 3-dimensional coordinate axis. And you could imagine now that I've got this hyperbola in the y direction. And so what happens is I'm extending it in this missing direction. And it extends all the way down. And there's another sheet to this hyperbola down here. Cylinders are very common and simple, and we'll make use of them a lot. We're going to move on to more complicated surfaces that can't be represented as cylinders. In our case, these are going to be called quadric surfaces. Now, quadric surfaces in some way are related to conic section curves that we talked about before. We are going to see a lot of equations that have 3 variables, and perhaps in some cases they're all squared. Or you could have 2 of the variables squared and the other one not squared. And you could cycle through the x and the y and the z for all of these particular cases. We won't get into cubic or any higher. Because these are surfaces, these are curved sheets of paper. What I am going to do is highlight some basics on how to visualize them and how to understand them, and then state some results. We're going to talk about something called an ellipsoid. Now again, I mentioned that these things are related to the conic section form, and a lot of the names will be similar. There's a typical equation for an ellipsoid. It looks something like this. It's got the x, y, and z terms all squared, no single or linear variables only, and it equals 1. A specific case of an ellipsoid where I've got x squared plus 4y squared plus z squared is equal to 4. This is not in the standard form. I want to put it in this standard form to be able to understand it a little better. So what I'll end up getting is x squared over 4, y squared over 1, z squared over 4 is equal to 1. The best way to try to visualize this is with traces. And traces are when you take coordinate planes and you intersect the surface and try to see what the resulting curve is. So we're going to start with the z direction first. So let's talk about z traces, 2, 1, 0, negative 1. And we're going to continually refer back to this equation. So I'll talk about the z equals 2 plane. I'm going to substitute the value of z equals 2 into the equation. I'll have x squared over 4 plus y squared over 1 plus 1 is equal to 1. Those ones cancel out. I'll have x squared over 4 plus y squared is equal to 0. This is only true if x is 0 and y is 0. So if this is the z equals 2 plane, this surface is just a dot in this plane. Talk about the z equals 1 plane, I'll have x squared over 4 plus y squared plus 1/4 is equal to 1. If I reorganize this, I'll have a 3/4. Now this is equation of an ellipse, but it's not in standard form. So I have to divide everything through by 3/4. I'll get x squared over 3 plus y squared over 3/4 is equal to 1. This is the equation of an ellipse. It's got a bigger number in the x denominator, y and x. This means the ellipse will be stretchier in the x direction. When z is equal to 0, I'll have x squared over 4 plus y squared is equal to 1. This is another ellipse again, and it is in standard form. And as before, this is a larger set of numbers in the denominators than I had in the previous case. Z equals negative 1. This is going to be exactly the same as what happens when z was equal to 1. Now, what I'm doing here, I'm just vertically going down through this surface, and I'm trying to see what it does when I intersect with various different heights. If I talk about y is 0 and plus or minus 1 traces. So remember, the equation of this ellipsoid was given by this. Now, if y is equal to 0, I'll have x squared over 4 plus z squared over 4 is equal to 1. This is a circle of radius 2. I'll have z and x like this. When y is plus or minus 1, what I'll end up getting is x squared over 4 plus 1 plus z squared over 4 is equal to 1. That means it's only true if I have 0, 0 as a point. So in this particular case, if I were to take traces in the x direction, it would be exactly the same as the z case above. The variables would change, but nothing else. Now note, for the x equals k or the z equals k traces, there's going to be no solution if the size of these things is greater than 2. So for example, if I had z is equal to 3, I'd have x squared over 4 plus y squared plus 9 over 4 equals 1. Well, this is going to produce a negative 5/4 on this side, and it's impossible for two squares to give me a negative value. So what are we supposed to do with all of this? If I were to think about a z plane, what we found, we always got ellipses. Now remember that the y direction was like this and the x direction was like this. If we were to talk about the y traces, remember that we ended up getting circles. And finally, if we thought about the x equals constant plane, we also ended up getting ellipses. So how am I supposed to put this all together? Imagine that these planes can slide up or down or in or out or back and forth, and you're trying to now reassemble a picture of this entire surface based on those planes. You'd end up getting some sort of football type shape. you'd have some sort of shape that looked like this. And depending on which way you walked, you would see a different thing. Now, this is an ellipsoid. If I were to slice this up and down in the z direction, it would produce ellipses. If I were to slice it through the x direction, it would also produce ellipses. And if I were to slice it through the y direction, it would produce circles. This is the strategy for how we can visualize these types of surfaces.